Okay, let's dive in. We're going to break down one of the most elegant, most reliable algorithms ever designed, merge sort. Seriously, this thing is a cornerstone of computing. And by the end of this, you're going to see exactly why. I mean, think about it. We are just drowning in data. So how do computers actually sort all that chaos into perfect order? Well, merge sort is one of the classic, most powerful answers to that very question. It's a beautiful strategy for creating order out of, well, a mess. And to understand it, we've got to go back, way back, almost 80 years, to the legendary mathematician John von Neumann. He first came up with this idea back in 1945 while working on one of the very first computers, the EDVAC. So you got to ask, right? What makes an 80-year-old idea so special that it's still a cornerstone of modern computing today? I mean, that's incredible. Well, the genius of it isn't in some super complex math. Nope, it's all about a beautifully simple strategy, a strategy that makes it incredibly efficient and, importantly, predictable. And that strategy, it has a pretty cool name. It's called divide and conquer. The approach is actually super intuitive when you think about it. Instead of trying to solve one giant, messy problem all at once, you just break it down. You chop it up into tiny, manageable pieces, solve those easy little pieces, and then just combine the solutions back together. Simple. So this whole process boils down to 3 simple steps. Step 1, divide. You split the unsorted list into 2 equal halves. Step 2, conquer. You recursively sort each of those smaller lists. And step 3, combine. You merge the 2 sorted sublists back into one single sorted list. That's it. Divide, conquer, combine. Okay, so that's the theory, but what does this actually look like in action? Let's visualize it. All right, so first step is the divide phase. We start with our big unsorted list, and we just keep splitting it in half. And then we split those halves in half, over and over again. And this splitting keeps going and going until we're left with a bunch of tiny lists that have only one item each. And here's the key. A list with only one item is, by definition, already sorted, right? You can't get any more sorted than that. This is what's called the base case. It's the simplest possible problem to solve. Okay, so everything's broken down. Now comes the really cool part, the merge phase. This is where the magic happens. We start combining those tiny, already sorted lists back together, 2 at a time, making sure they stay perfectly sorted every single step of the way. And here you can see the whole journey, from top to bottom. See how it divides everything all the way down to individual pieces? Then the merge phase kicks in, and it starts systematically combining them back up. With every single merge, it's just looking at 2 lists, picking the smaller element, and putting it in the new list. It does this over and over, building bigger and bigger sorted lists, until, bam, you're left with one single, perfectly ordered result. So we know how it works, but why is it so good? What makes it so special from a performance standpoint? Well, to measure how good an algorithm is, we usually look at 2 key things. First, how fast is it? That's called its time complexity. And second, how much extra memory does it need? That's its space complexity. Okay, so the time complexity of merge sort is what we call O of n log n. Now that might sound a little technical, but trust me, in the world of sorting, that is the gold standard. It basically means that even if you throw a massive amount of data at it, the time it takes to sort grows really predictably and efficiently. You don't get those sudden dramatic slowdowns that you might see with other algorithms. So where does that n log n actually come from? Well, think about it. The log n part, that's just the number of times you have to split the list in half to get down to those single elements. And the n part, that's the amount of work you have to do at each of those levels to merge everything back together. So you're basically doing n amount of work log n times. Simple as that. But, there's no free lunch. This incredible efficiency comes with a trade-off, and that trade-off is memory. See, some algorithms are in place, meaning they can just shuffle data around inside the original list. Merge sort, well, it can't do that. It needs some extra workspace. Specifically, it needs a whole separate temporary array that's just as big as the original one to help with the merging process. And this gives it a space complexity of O of n. All that means is that the amount of extra memory it needs grows in a straight line with the size of the list you're trying to sort. More data, more memory. Okay, this table really puts it all into perspective. Look at merge sort. See that O of n log n across the board? Best case, average case, worst case. It's always the same. rock-solid consistency. Now compare that to something like Quicksort. Yeah, it's fast on average, but look at that worst case, O of n squared. That's way, way slower. And that predictability, that guarantee that it will never have a terrible day, that's what makes MergeSort so incredibly reliable. So, this isn't just some dusty old algorithm from a textbook, okay? Let's talk about where this nearly 80-year-old idea pops up in the technology you and I use every single day. I mean, this is serious, battle-tested code. It's running inside some of the most widely used software on the entire planet. We're talking about programming languages like Java and Python. Heck, it's even used in the very core of the Linux operating system. And that reliability is exactly why developers trust it for critical stuff. Applications where a worst-case performance meltdown is just not an option. It's also something we call a stable sort. That's a key feature. It means if you have two equal items, it keeps them in their original order. That's super important if you are, say, sorting a list of people first by city and then by name. You don't want the name sort to mess up your city sort. So it brings us back to that question. In an age of just raw, brute force computing, is an elegant idea still the most powerful tool? Well, I think MergeSort is definitive proof that the answer is yes. It shows that even in a world obsessed with just throwing more power at a problem, a clever, well-structured approach from decades ago can still be the most powerful and most reliable tool we have for bringing order to chaos.